Good afternoon. My name is Ali. This is Harish, and two of our other group members, Kavish and Kissan, are manning our booth. And today we're going to talk to you about a coating we have developed called Nanotize, which we have surface activated to be both antimicrobial as well as be superhydrophobic. And our consultants on this project were Dr. Tam and Dr. Gu. So through this presentation, we will first take you through the main issues we face and current solutions that are available on the market that tackle it. We will then talk to you about our coding, its synthesis, and its application methods. And then we will go over the experimental results and just a cost comparison with other people on the market. So healthcare-acquired infections is a general term that refers to any disease that a patient can contact while they are accessing a health service. And we have found that this is due to inadequate cleaning. And some common examples would be influenza, HIV, and pneumonia. In fact, the risk of HAIs runs at up to 10.5%, which means that this year alone, 220,000 people in Canada will succumb to it, and leading to about 12,000 deaths. So just to emphasize this point, 32 people will die in Canada today because of a disease that they acquired from going to a hospital. And in fact, it's such a severe epidemic that it's been ranked as the third largest cause of death in Canada, behind heart disease and cancer. And just to put a dollar figure on it, the Canadian government currently spends about $4.5 billion on this every year. So this diagram here shows you the general life cycle of bacteria formation on a surface. So we start off with stage 1 here, which is the initial attachment. And here we have the temporary adhesion of bacteria to a surface. Now, even though the bacteria may come and go, they leave behind this green residue here, which has been deemed crucial to further stages in the bacteria life cycle. This is followed by step 2, in which the bacteria adhere to the surface on a more permanent basis. Step 3 is the microcolony formation. And here, basically, the bacteria come together, reproduce and multiply, and the size of the colony on the surface keeps growing. This is followed by step 4, which is the biofilm formation. So here, the previous microcolony that was formed is now covered in this protective layer across the surface, which just gives you the optimal conditions for further bacterial growth inside. And it is at this stage where removing the bacteria from the surface becomes really hard. In fact, 100 times harder than these initial stages here. And this is why we have designed our coding to work at the beginning, to completely avoid the problem at the end. Lastly, on the right, we have stage 5. This is the distribution phase. And here, the biofilm ruptures due to excessive mass, and this just leads to spread of bacteria. And the reason why this is really severe is that up to this step, the bacteria was localized to the surface, and now it is able to leave and impregnate other surfaces. And we believe that this is where HAIs become most probable. So in designing a product that is aimed at the healthcare industry, we came up with a list of desirable attributes we would like our coating to have, namely high durability, potent antimicrobial activity. We want it to be low cost, as well as be applicable to a wide variety of surfaces, just to make it versatile. We then took to doing some market research to see the approaches that other people had in tackling the same issue. And this generally fell into two main categories. So firstly, we have the superhydrophobic sprays such as Neverwet and Hydrobead. And basically, these aim at preventing surface wetting. However, these solutions are currently not used in hospitals. Next, we have antimicrobial agents such as disinfectants and germicidal agents. And these aim to kill bacteria on a surface. However, some of them have been known to be very toxic. And overall, none of them offer us a more permanent solution because both of them need to be reapplied constantly in order to be effective. So we have designed Nanotize based on both the approaches I just mentioned. So we use the phenomenon of superhydrophobicity to prevent the bacterial adhesion to the surface through protein binding. So we use nano and macro scale roughness to achieve a hierarchical structure. And because water forms such a large contact angle, it is able to roll off the surface and carry with it any residue that is left behind by the bacteria. So if you remember me mentioning earlier that the residue was key to further formation of the biofilm, we would cut that right down by having the residue washed off with the water. A clean surface, no bacteria growth. Say per chance the bacteria still was able to stick, we also have mechanism number 2, which is the antimicrobial activity. And we introduce silver nanoparticles into the coating to attack the bacteria. And the way this works is by permeating through the cell walls, and then they form disulfide bonds with thiol groups in enzymes. And this just disrupts regular cell processes. So the cell isn't able to respire or metabolize or reproduce anymore, and eventually this leads to cell death. And not only does surface silver offer us greater potency, it is also less harmful and less toxic than free-flowing colloidal silver in solutions. So this is what we have designed our Nanotize coating to look like. We start off with a substrate that we would like to coat. We then deposit a layer of adhesive on it. And for this step, we have been able to use commonly available adhesives from the local hardware store. And lastly, we deposit our layer of Nanotize to the surface to complete the coat. This just takes a couple of minutes to dry, and it's good to go. And this Nanotize coating is made up of 3 key components. So we have the large silver spheres, which represent titanium dioxide nanoparticles. And we have them in a variety of sizes to be able to tune the surface roughness. We then coat it with a hydrophobic polymer. That's the orange squiggly lines. And what that does is just improve the superhydrophobicity. And lastly, we have the silver nanoparticles in blue. And they are photodeposited onto the TiO2 to give us the antimicrobial agent. So the coating that we've designed can be applied in a variety of ways. It can be dip coated, it can be painted, but more importantly, it can be sprayed. And in experimenting with these processes, we were able to look at a few commonly available adhesives, such as the Super 77 spray, a Scotch Weld super glue type of material, and contact cement. And we found the spray process to work best. And later on in the project life cycle, we started experimenting with a one-coat spray. So this is where we were able to add the adhesive to the solution matrix and just coat once. So if I can draw your attention to the animation here, we take a plain substrate, in this case stainless steel, and using our spray, we can coat it once. This solution would take approximately 2 or 3 minutes to dry, and then it is good to go. It's a permanent coat. And lastly, we identified a few design trade-offs based on the coating we had come up with. And these generally revolve around the concentration of active material that we use. So for example, the superhydrophobicity could be increased by dip coating as opposed to spraying. However, this leads to a decrease in durability as well as transparency. On the other hand, the antimicrobial activity can be increased by increasing the concentration of silver. But again, this was at the cost of transparency. So as a group, we decided to just completely get rid of transparency and concentrate on the other 3 because we prioritized the functionality of the material over the aesthetics. So I will now pass it on to Harish to talk to you about the experimental results.
So we applied our coating to a wide array of substrates. As you can see here, we have successfully transformed glass into a superhydrophobic surface. The contact angle is now greater than 150 degrees. Also, if you continue to watch the animation on the right, you'll notice that it's able to withstand a vigorous scratch test. After this scratch test, it remains non-wetting, and we don't see any leaching from the coating itself. Furthermore, I just want to point out that this coating was applied using the spray method. It dried within a matter of minutes. However, the coating is durable and it lasts for months. We had similar results coating metal as well. Once again, the surface is superhydrophobic after a simple spray treatment of our coating. And again, if you watch on the right-hand side, it's able to withstand the scratch test, remain non-wetting, and again, durable for months after. Now, we were also successful in transforming other surfaces into superhydrophobic platforms as well. You can see we transformed paper towel, latex glove, plastic, and wood into superhydrophobic surfaces. Now, in healthcare settings, common areas of bacterial contamination include the gowns worn by healthcare workers and bed sheets. That's why we decided to test our coating on cotton. As you can see here, we were successful. On the far side, that's uncoated cotton. It's easily wetted. But on the right-hand side, we take the same cotton and expose it to our product here, and it's able to remain non-wetting even after being submerged in the water multiple times. Now, in a hospital setting, there's many areas where contamination, bacterial adhesion, and growth can occur, such as experimentally inoculated tabletops, the gloves worn by the workers, but also sites very close to the patient, such as bed sheets, bedside tables, the bed rails. But since our coating can be applied to such a wide array of substrates, we have the potential to effectively eliminate all the common sources of bacterial adhesion and growth. We tested the durability of our product using the standard sandpaper and tape test. To test the adhesive properties of our coating, we applied 2 by 2 centimeters of Scotch tape to the surface, firmly pressed it against the coating, peeled it off, and remeasured the water droplet contact angle. To test the abrasive resistiveness of our coating, we applied weighted sandpaper along the coating, rubbed it along the surface 10 times, and then remeasured the water droplet contact angle. As you can see here, if you look at the green line and the dark blue line, the contact angle degradation is less than 7% after such a vigorous treatment. And these are not conditions that you would normally expect in a hospital setting. Furthermore, we also noticed a trade-off between superhydrophobicity and transparency. As you can see here, we were able to achieve up to 70% transparency while still retaining superhydrophobicity, but increasing the transparency further than that resulted in a significant loss in superhydrophobicity. But this isn't as we mentioned before, this isn't a key requirement, but it might be something that we intend to work on in the future. To study the antimicrobial properties of our coating, we monitored the growth of E. coli on a normal glass slide and a glass slide coated with our product after 24 hours. As you can see here, this glass slide here, there's significant bacterial growth after 24 hours. You can also see some bacteria on the glass slide itself. However, our coating here, there is no bacterial growth at all after 24 hours. And the reason we chose E. coli is because it's one of the most common gram-negative organisms, and gram-negative bacteria are known to cause pneumonia, meningitis, and bloodstream infections in healthcare settings. Furthermore, gram-negative bacteria are becoming very problematic because they're becoming resistant to your common drugs and antibiotics on the market. But here we show the potential to eliminate the growth of these organisms from even happening in the first place. We also determined the MIC value, the minimum inhibitory concentration of our nanoparticle, our silver TiO2 nanoparticles, to be less than 47.4 micrograms per milliliter. So what that means is silver is still able to retain its antimicrobial properties even after being impregnated in TiO2. And it puts us in the range of Lysol, which has a listed MIC value of 32 micrograms per milliliter. So currently it costs about $1.03 to apply our coating to 1 square foot area. And that puts us in the range of other commercially available superhydrophobic and hydrophobic sprays. But since the area of permanent antibacterial coatings is a research field that continues to grow, we intend to make ourselves more competitive on the market by decreasing our cost. We're looking at different ways of synthesizing our nanomaterials and using cheaper nanomaterials without compromising the performance of our product. So to conclude, healthcare-acquired infections is a serious problem here in North America. It results in about 32 deaths every day. We've tried to solve this problem using a sprayable, superhydrophobic antimicrobial coating that can be applied to a wide variety of surfaces. It's durable, it lasts for months, but it only requires application, it dries within a matter of minutes. It also clearly prevents the growth of E. coli. In the future, we would like to improve the transparency, or at least improve the final aesthetics of the final coating. We also want to work on a few durability studies using our one-step spray method. We're also trying to study the difference in durability depending on the substrate you intend to coat. And we also want to do more thorough bacteria studies using different organisms, such as Staph aureus. Thank you for listening to our presentation. We have live demos available at our booth, so please come check us out. And if you have any questions, you can ask them now.
Yes.
So we have a two-step spray and a one-step spray. So
Are you making the spray?
we are making the spray. Like,
How do you make the spray?
so the two-step coating, for the two-step coating, we use commercially available adhesives, such as 3M77. You can pick it up at your local hardware store. You just spray it on any surface. Well, it works best on wood, metal. And then we apply our coating, which can be sprayed. Our coating consists of the TiO2, the silver, and the polymers. Yes.
Yes.
Yeah, was that video of your spray?
Yeah,
Yes,
that's ours.
That's our spray.
So how do you feel it, the spray can? How do you make that, spraying?
The can itself, we didn't build a can.
Well,
but
of course I
yeah.
understand that. I'm asking, how do you feel that? How did you have to actually put the gas in?
Oh, no. So we actually found it's already available at Home Depot, and they use it for home retouch-ups. So they already have an aerosolized can with just a beaker at the bottom where you can put your solution in there, and it sprays an aerosol.
That's what,
Yeah.
that's what I figured. Some of
Yeah.
those-
So the coating we actually make is in solution form, and that's why you can dip coat it and paint it and do whatever you want. But with this application, you can now spray it onto surfaces as well.
Right. That's
Yeah.
a nice solution. I mean, because you can use sort of already ready, sort of
Yes.
application ready,
Yeah.
spray cans. And so there is some kind of attachment basically where you put your liquid and then use your spray to kind of.
Exactly.
Right.
Yep.
And the second thing, how you hydrophobic the compound?
So there's two ways. We're focusing on getting hydrophobicity by introducing a micro-nanoscale roughness. So that's by tuning the size of the... Yeah, so that's when we apply the spray, the surface, because of the different sizes of the TiO2 nanoparticles, we think it's forming a rough texture.
So that's hydrophobic.
That itself should introduce enough surface roughness, but we do have a polymer coating on top. We are not completely dependent on the polymer coating though. So in the case of like grease or oil attaching onto the surface, it's not lipophilic, so it should still withstand that.
So you are really hydrophobic. Looks like from the results.
Yes.
Yes.
Yeah.
So you have a trick to achieve it, or you just buy the rough surface and achieve it, or you have some ingredient in your system. So the top surface is your material.
Yes.
So why is it so hydrophobic?
So if you could go back
Sure.
to that slide with the hierarchical structure.
Absolutely.
Yeah.
Do you have flooring or some
Yes.
Yeah. So the
flooring
I think it's lagging.
and the nanostructure, flooring plus nanostructure?
yeah. So I mean, while it's lagging, so
That's the secret recipe. Nano.
Right here. Oh, keep going.
So you have a hydrophobic flooring polymer.
It's polymer, I think, basically.
Yeah. So again, coming back to this diagram here, if you look at if you notice the size of the silver spheres, they change. So for this coating, we were able to use 3 different sizes, and this just gives us the surface roughness. In the micro scale, in the nanoscale, it is introduced by having the silver nanoparticles on top, so it forms a really bumpy structure. And then just to add to the effect, we have a fluorosilane polymer, and this just takes it to the next level to make it super hydrophobic.
So is it, I'm sorry, is the polymer that makes it mostly, is responsible mostly for being super hydrophobic, or it's the roughness?
So we haven't done a complete set of studies to determine what it is. Ideally, we are hoping it is the the micro nanoscale roughness introduced by the tuning of the
I would think the other way around. I thought that it's your polymer endings that actually help, but maybe I'm wrong. I'm asking you.
Right. We don't want to be completely dependent on the polymer though, because polymers will degrade over time.
Right. And so roughness mostly helps you with hydrophobicity. Is there other functionality of roughness that matters to you? Because often people use rough surfaces for different type of applications. You know, one thing that I see as a problem, when you have a rougher surface, it means you potentially have more sort of binding sites for your bacteria and such. To me, that would be almost like a little bit counterintuitive in terms of sort of the surface, you know.
That is something that we didn't quite realize until midway through the project, actually. But the thing is, that's where the fluorosilane helps a lot. Fluorine groups, I think fluorine coatings are actually used quite often in marine applications. It prevents biofouling. And the thing is, with superhydrophobic surfaces, it actually prevents bacteria from attaching via protein binding. So that's where the whole
So that's what I'm saying. You know, I'm saying basically when you have a rough surface, your protein absorption tend to be pretty.
And that kind of just motivates us to use the nano silver as well. I mean, protein binding we can definitely stop from happening.
Right.
But say there was any other form of binding, we actually have a live antimicrobial agent which is actively working as well. So we should be able to stop anything else.
Did you do a comparative study where you used only one size of titanium and your polymer? And how would that compare?
So that we haven't gotten to yet. I mean, just developing this has been quite strenuous, especially with the sprays. And this is just something that we want to work on now. So like you mentioned with extra bacteria studies, this will be one of them to see which component in the coating is offering us the best properties and how we can tune that just to make the product cheaper.
Do we have time for one final question?
Yeah, I have a question too. No,
Please,
we have
go ahead. I'll come at the end.
no, because we have a buffer of 20 minutes after the next presentation.
Okay.
Okay.
We have time.
I want to get back to spraying. So it has silver nanoparticles in it, right?
Yes.
And you're not spraying that in a fuel wood. So it makes me very nervous that these nanoparticles are going into the air. So
Right, so they're immobilized. They're immobilized on the TiO2, and they should not be leaching off the TiO2. And the mechanism that we're using to kill bacteria is contact mode method. So if the bacteria adheres to the surface, silver ions are leached out, but the silver nanoparticles itself should remain on the TiO2.
how big are the TiO2?
So the TiO2, most of the particles are greater than 100 nanometers in size. So
It's still pretty thin particles of that size.
we were very safe. We made sure we were not exposed to these nanomaterials. Everything was done in a fume hood.
Yeah.
Your video is like a little, but
No, it is. It's just that the video camera is kind of taken to just where the sash comes down. And again, for application in the real world, which is something that we want to work on as well, would be, I guess, by wearing masks just to prevent the inhalation. And again, further immobilization of the nanoparticles is, again, something we want to work on.
And just to point out, the TiO2 that we use, it's mainly rutile TiO2. And rutile TiO2 is used in sunscreen and makeup that people rub all over their faces, and which we're not doing at all. So it should be safe if it comes in.
there's different nanoparticles on it.
Right.
And you don't want any bacterial
Yes.
stuff inside your body, I would think.
No.
I'm not even sure, say if you have anatase instead of rutile, is there any evidence that that's more harmful at all?
So-
I agree with Irene. I think I'm more worried about the silver particles
Okay.
than rutile versus anatase, you know?
So the only thing we could find about anatase was the fact that anatase is more difficult to remove off your body once it attaches to your skin. But that's all that we could find with regards to anatase.
Yeah, I mean, anatase is a more efficient photocatalyst, and there are all kinds of other properties of anatase relative to rutile, but I'm not sure that safety-wise it matters.
Oh, and again, just coming back to it. So we started working with TiO2, and we realized that TiO2 is only active, especially in the anatase phase, in the UV range.
Right.
And we want something that works continuously. It would defeat the purpose if you coated your hospital wall with anatase and then have to take a black light to it at the end of every day
Correct.
to get the
Each
antibacterial.
anatase is
right?
more, responsible
So-
to light,
Yeah, so at this point, the titanium dioxide is just forming the base for the superhydrophobicity. It doesn't actively take part in any bacteria killing. That's just left to the silver.
I understand that.
Yes.
Do you have a calculation for this structure? You said it's better to have the small particle together and one. Do you have a calculation?
So unfortunately, the SEM was down when we went to use it. We would like to actually get an image to make sure, just to know what the surface looks like. But the photo deposition method itself, we're using a very common method that's known to work, silver being immobilized on TiO2. It's been done multiple times. So we're confident that the silver is on the TiO2 itself.
Yes.
Right.
Yes.
But we did do, in terms of characterization, our bacteria studied of just the TiO2 silver nanoparticles. That showed that there was antimicrobial activity, which means there should be silver on the TiO2, because TiO2 itself doesn't have antimicrobial properties without being activated by UV light.
Anything else we can answer?
Okay, can I ask one more question?
Sure.
First of all, can you remind me again how you deposit silver particles? You said it's a gas phase method or a
Photodeposition.
photodeposition?
So we have a slurry with a TiO2 and a silver salt solution. We expose it to UV light, and due to the electron hole pair created by TiO2, that allows silver to be absorbed onto the TiO2 surface, and then it grows over the.
It's not just to be absorbed; it has to be reduced because you're starting
Right.
with silver salt, and it has to be reduced
It-
to metallic silver,
Right.
or metal silver, right? So is that more of a reducing agent or more of a sort of? I don't think how I don't see how absorption would change. I would see that by exciting, essentially forming an excitome, you can do photochemistry. You can do redox chemistry, but I'm not sure that you can actually help absorption.
No. So when the silver salt solution is being mixed with the TiO2, any silver ions that have been absorbed onto the TiO2 will be reduced due to the electron hole
So you
pair.
don't have an additional, reducing agent in the mixture.
We don't, right?
No, we
No,
don't.
no, we don't. No.
Okay. And so one final question on your slide 18, you visually showed the lack of bacteria, once you deposited your spray. But there may not be a quantitative study, and it's done only after 24 hours.
Right.
How do you know that within some prolonged period of time,
So.
there may be
Yeah.
essentially residue that will eventually build into
So yeah, we definitely need to do a more thorough bacteria study, and that is definitely on our radar. But I want to point out the incubation period was 24 hours, but these images were actually taken a week after, and we don't see any growth around the coating.
A week is a more sort of
Yeah.
reasonable amount of time. I
Right.
agree, but these things are supposed to sort of kind of have an activity for a prolonged period of time. That's kind of my point.
Right.
And again, the reason why we stopped at this phase is that this is already an ISO protocol, and we were able to get results that were comparable to already really well-working products such as Lysol. So once we got to this phase, and after a week we saw no further growth, we were happy with the result we had here and kind of stopped here to work on development on the other phases of the project.
I understand time
Yeah.
is limited. I
Exactly.
understand the limitations of these
Yeah.
projects. It's not unreasonable, but I'm just posing that as a question. But nice work, and you guys defended this to the best of your ability. It's good stuff.
Thank you.
Good stuff. Okay.
Thanks.
I'm done, but you guys.